Good morning all. New printed circuit boards from JLCPCB, and these are the first ever 4.0. That's interesting. That is a mobile holder, which I presume has been laser cut from cardboard. Have a look at that later. 4-layer printed circuit boards. First time I've ever made a circuit board with 4 layers of copper. So let's take a look at these. Now the 2 inner layers don't have any tracks on them, they're just planes. And I've allocated them. I was just wondering whether we could see those inner layers. Oh, possibly. Yeah, possibly we can see those inner layers. Not quite sure. So I've allocated the 2 middle layers to plus 12 volts and minus 12 volts because this circuit board has an op-amp on it. The bottom layer is 5 volts, I believe. I believe this is a 5 volt ground layer. And these tracks here go to LEDs and they use the 5 volts. So I've put them on the bottom layer. And then on the top layer, I've got the tracks that go to the op-amp, which are the sensitive audio tracks. And they run through another ground plane on the top layer, which is ground, so that they're in effect shielded by this ground plane. So yeah, 4 layers, ground, plus 12, minus 12. I've no idea which layer they're on. I don't suppose it matters really, as long as they go to the right pins on the chip. And on the bottom, I've got 5 volts, which is going to run this single inline chip, which is a KA2284, and that's a 5 LED bar graph chip. So this has got an op-amp with a filter. We'll feed some audio in here, and we should see the bar graph bounce up and down. So this is another of my concept PCBs. This one, the idea is that it's for any large-scale circuit which grows in a sort of matrix form. Now that's the underside, so I'll have my op-amps at the front. So this is essentially a section of the vocoder, but I'm implementing it as an audio spectrum analyzer, and this project is going to grow sideways. Oh, sorry about the reflections there. And just carry on growing out like this. And when you've got a project like this that is going to expand in all directions, it will also grow this way as well, but that'll be a different board with possibly more op-amps and a different set of connections. Where you've got a project that grows like this, you really need to be mindful of power distribution. And so the idea is I've got these 8-way connectors. They're just pads for DuPont headers, and you can daisy chain them this way, and you can also daisy chain them this way. So there's a common set of connections here. I think on the outside of each one of these 4 connectors is 5 volts, so we should find that the outer 2 pins on every single one of those connectors is spoked into the 5 volt ground plane, and it is. So 5 volts is distributed on these outer 2 pins. I used 2 pins because I figured 5 volts may get quite a heavy load on it, and so that's just for current really. The inner 2 pins are audio, so here they're audio in, here they're audio out. I think they're commoned on this design, or one is used, I can't quite remember. Actually, I think they are commoned. Yes, you can see they're linked together up there. So this is audio in, that's audio out to the next stage of the circuit. The 2 pins either side of the signal pins are ground, so they should be spoked out. Yes, they are. They're spoked out onto my ground plane. And then the pins, 1 in from each end, are, well, one of them is plus 12 and one of them is minus 12. And so all of those power supplies are daisy chained throughout this system, which, as I say, will just, if I move those there, I'll get that reflection, will just grow and grow and grow. So these 10 boards will be for 10. What's that? That's a little thing crawling up my arm. I think it was a fly, not a spider. No, it's a tiny spider. So yes, these will just be 10 different filter frequencies, and therefore the bar graphs will be a spectrum analyzer at different frequencies. So as you change the frequency of sound, like ew, then you should get a sort of run up and down this thing. That's all I'm going to build with these boards. Later on, I might possibly build a full vocoder using this technique, but it probably also lends itself to my 8-bit computer, because again, that's a circuit which is going to grow in all directions and requires very careful attention to power distribution to ensure that it's there in enough current quantity for every part of the circuit to function properly. So I just wanted to do some continuity checks. I know, for example, that pin 4 of the op amp is minus 12 volts, so I can check that that appears on one of these 2 pins on all 4 of the connectors. Right, this meter is the one with the loudest beeper. I hope you can hear it. Right, let's try pin 4 of the op amp. Now it's coming from this side. And that should connect to one of the either 2 or 7 on this connector, and it is pin 2. And I think the idea of that was that it's on this side, so that it runs up on the side where minus 12 volts is going to be used. So pin 2. So that inner layer certainly is connecting those 2 pins. Now it should also go to pin 2 there, pin 2 there, and pin 2 there, which it does. So that's good. Now let's try pin 8 of the op amp. Oh, you can't see the meter, but you don't really need to see it anyway. So that should go to pin 7, which it does. That's fantastic. And 2 shouldn't connect to 7 because they're separate power planes within the board, and it doesn't. So back on pin 8, 7, 7 there, 7 there, and 7 there. So that's fantastic. The power planes, plus 12 volts and minus 12 volts, are the 2 middle layers, and they certainly do seem to be connecting up correctly. 5 volts are these outer ones, so they should all connect together. And like I say, 5 volts is visible, or at least 5 volts is this copper plane on the bottom. I wanted 4 copper planes because I wanted a ground plane on the top through which the signals ran, a 5 volt plane on the bottom for current primarily. I figured, I don't know whether this is the case or not, that the copper on the bottom might be thicker than the middle layer copper, but I don't know. It may be all the same thickness. And plus and minus 12 are on the center layers of this PCB. I thought you'd like to see this in EasyEDA because it's the only place we're going to see the center 2 layers. So here's the design. Blue is the bottom layer, so that's on the 5 volt plane. Red are the audio tracks, they're on the top layer. That's where the ground plane is. And the inner layers, it seems you have to come up to the layers thing, select inner 1, and then you can actually select that, and you get some properties up here, and you can see that the net for inner 1 is minus 12 volts. It's solid, you've got the choice of solid or no solid, but that's about it. What you don't have are things like clearances around pads and spoke sizes. They appear to be fixed. Now you can see the spokes here if I zoom in. So on the top, for example, you can see that on the minus 12 volt layer, you can see the clearance around this pad, the minus 12 volt pad, and the spokes. If I switch to the other layer, inner 2, and click that, then the spokes are here on this plus 12 volt pad, and it just spokes where it connects to that particular pad. So one other place you would expect to see this is pin for plus 12 volts would be pin 8 of the IC, and there it is. and you can see spokes around there and spokes around there. But again, only controls appear to be the net name and whether it's solid or no solid. And actually, even if you select no solid, it doesn't appear to change. I mean, if that's a crosshatch, it doesn't show it. So the controls seem quite primitive, but well, certainly it works because we proved that from the continuity tests. The only other hint at the inner two layers you get is in the 3D view, and this is very slow on my computer, I'm afraid, but you do get the merest hint of these two lines down here. They'll clean up in a minute, which to my mind hints that there are two inner layers. Now, they may not be positioned exactly how this shows them, but we've got a top copper layer, an inner copper, an inner upper and an inner lower, or layer 1 and layer 2, and of course the bottom copper layer. But that's about all I can find. Oh, look what I found. If you put some distance between the layers, you can actually see the silk screens, the copper, the bits of board, and you can turn these on and off. So if I turn off the silk, the top silk layer, let's turn off the top solder mask. But by switching on and off some of these layers, we could conceivably go and have a look at the inner copper layers. Actually, I'll try and do that now. So here I've switched everything off except inner 1, and yeah, you can see a rendering there of the copper on the inner 1 layer with all the clearances and spokes onto the pads. I think that's a decoupling capacitor, and this is the negative 12 volts of the op amp. Yeah, you can see a rendering of the copper for the inner 1 layer. And on this 4-layer PCB offer, $2 for 4-layer PCBs, limited time up to December the 25th. $2 if you have boards less than 50 millimeters and 5 pieces. 10 pieces goes up to $7, and if your boards are bigger than 50 mil up to 100 mil in both dimensions, I believe, 5 pieces will cost $7. And I'll put a link in the description below to this page. So taking this concept a bit further, my idea was that on the baseboard you'd have all the power distribution, so it's on all 4 sides, and I did try laying this out without 4 layers, but JLCPCB have actually got an offer on 4 layers at the moment, so it made sense to go for 4 layers. And in fact the layout is completely trivial when you use 4 layers. When I was running on 2 layers, of course, I had to try and link all these power connections up, and I had tracks everywhere, vias everywhere. It's a lot easier on 4 layers. I mean, you can see there are very few traces on here at all. So the idea is that chips and power distribution go on the bottom layer, because typically chips, ICs, don't interact with the user. And then there would be an upper layer. And the way this would work is that, and I've made a little mock-up on this green prototyping board. I used 6-pin female JST sockets, and then plugged into them would be a top board. And the top board would have things like LEDs, so anything which interacts with you visually. It might have DIL switches if this was a digital system. It might have potentiometers, which this has got to set the gain on this filter. And also anything which is swappable. So for example, I might want to swap these filters around, and therefore this filter board can be taken out of this position and moved into other positions. Other things that might be on the top might be connectors, for example, so that you can connect things in on the top layer, but typically silicon doesn't really interact. I mean, I know there are a few ICs, there are some light sensor ICs which would have to be on the top layer, but I wanted this to be a dual layer design using off-the-shelf Arduino style connectors. So these female headers, 6-pin particularly, are very common because they're an Arduino size, and of course the DuPont male headers. I wanted it all to be built out of these very common, and as a result they're quite cheap, parts that you can get on eBay. So in this particular instance for the audio analyzer, my top board here has a user accessible potentiometer, so that's on the top. It has a filter which may need to be swappable, so that's on the top. And the top board here is going to have 5 LEDs on it. It's a sort of mini bar graph, like I say, the KA2284. So to start assembling this project, I need to probably start by putting some turned pin sockets down here, or strips. I'll put a single strip there for the KA2284. I'll put in 2 strips here for a dual op amp, a 1458. And then I need to check that there's enough clearance under here. Now there should be, even with this board that I've made on proto board, and it has quite a lot of under clutter on here because you tend to have to route your traces, because this is just a matrix of holes, route your traces using actual physical copper wire, the component legs typically. So I just want to make sure that all fits. So I'm going to go and get an op amp and some turned pin arrays, and let's get soldering. I wonder if this mobile phone stand is butch enough to hold a DVM. That'd be interesting. So I presume that goes through there in some way, and that sits like that. Yeah, that must be it. Let's give it a try. Yeah, it kind of works, but actually this meter's a little bit big to sit on this shelf, and it's a bit heavy, so perhaps I'll stick to using it for my mobile phone. Oh, just one other thing I meant to say, this board is exactly 1 inch wide. Now that might be a little narrow for some things, but I did manage to fit 2 ICs on here, a bit of decoupling, the positions for the female headers to come up to the top layer, and all the interconnects so that you can create a matrix of this. The original idea was to make a board that was, that's my meter, 1 inch square. So actually what this is it's 1 inch by 2.1 inches on the basis that these would be set 0.1 inches apart, and so the matrix would be based on a 1.1 inch repeat. I just liked those numbers. So I've got some turned pin strips here. Now when I originally designed this, fortuitously I put this row of connectors 0.1 inches from the edge of the board, and if I'm going to have this 0.1 inch gap, that does mean that the distance between 2 boards, or these 2 rows of pins, is 300 mils, which is coincidentally the pitch of an IC socket. I was just wondering, I know it's a bit of a wacky idea, whether you could use IC sockets to link these boards together like that to create the matrix, and then jumper across here. Now I've got some, and they date back a long way, these things, which are little 300 mil jumper links. So let's break off 2 strips of 4 for my op amp, get that soldered in, and just check the height underneath my top layer module there. Yes, everything's quite tight actually. The IC sockets at 300 mils, these female headers at 500 mils, pretty much touching them, and then the height clearance it's actually not quite there. Doesn't matter too much because I'm thinking of redesigning this top board as a printed circuit board, in which case it wouldn't have that stuff underneath. So yes, I think essentially this all works. Okay, oh, the KA2284 actually is quite a high profile component. There's one in here. So yeah, that might not be able to go in a socket because it is very tall. Yeah, much taller than the op amp. So I think in that case I won't put it in a socket. I'm going to have to solder it straight into the board. Oh well. So as luck would have it, I found this elastic band which can hold that in while I solder it. Let's do that. Yep, that's up to temperature. So let's get this 8-pin chip in. Try not to melt the elastic band while I'm doing this. Can I see what I'm doing? Just about. Right, that's the 8-pin chip soldered in. Now you can see what I mean by how tight this is. I can't actually lower this down with the top board on these connectors, so I'll have to take these off, put them in separately, and then reattach this top board just to hold everything square, and now solder these female headers. I don't need these long ones, but they're the only ones I've got, so they'll have to do, and I'll have to clip them off. Okay, let's solder these. Tricky with them being so long. I'll just do the end ones for now, because then I can pull my module out and do it lower down. So here, for example, on this module, minus 12 volts and plus 12 volts go to the chip, but they don't actually run up. What I did was I put 6 connectors either side, so you've got a couple of extra points so you can run signals up. Now one of the chip pins happens to be ground, so that one runs up and the ground distributes around this board. But and one of these end pins I think is the signal going in and one is the signal coming out. But the passive components on the top don't actually need plus and minus 12 volts, so they don't go up these 2 female connectors. Now, like I say, there's not enough headroom to put the KA2284, which is the 5 LED bar graph chip, in a socket, so I'm going to solder that straight into the board. And I haven't yet actually made a top board. I'll do it with this, it's 6 holes wide green prototyping board, which you can snap very easily across a row of holes. I'll build it on one of those to sit on the top, and then that is actually a complete module. But let's get that 2284 soldered in. Now, as I say, I haven't made a top board with the 5 LEDs in it yet, so I'm just going to use this board again. These are also 6-pin headers, just to solder that in so it's ready to take a top board, and solder the remainder of these pins, which is made harder by the fact that they're really far too long. You can of course get these female headers with much shorter pins. So I think that's probably it for this video. It's probably got quite long already. So what I'm going to do is make up my LED top board to sit on top of the LED driver chip, and then I'll make another video showing this thing and put power to it and put an audio signal into it. I might build 2 actually, because that's the only way we're going to see the difference between the filters, so you can see how they vary in terms of the bar graph strength, and actually try and get this thing working. But for the moment, cheerio.